Okay. Okay, very good. Thanks. Okay. Good. So today marks a big transition in terms of the flow of this course. A transition between the two major sorts of modeling that we're going to be looking at, as well as a transition between some of the modes of interaction in the course, with greater recourse to some pre-recorded videos for some of the more standard stuff, and use of the class time for some of the exercises we'll be pursuing together. So within today's lecture, I'd like to lay a bit of a motivation for this shift of perspective, give you some sense of what's involved when we're changing perspective in this way, some sense of the new lens we'll be using, and as time allows, we may do some work together using any logic to explore at an early level the building up of agent-based models. I sent late last night, later than I would have liked, a hot off the press exercise, in which I challenged you to build up a simple model, an agent-based model in any logic. This model was very, very simple by design. The dynamics were just about as simple as possible. It did exhibit some of the features of any logic in the presence of and the ability to represent heterogeneity, the ability to parameterize agents and main class. And if you haven't had time to pursue this, I'd like to request that you do in the next few days, so that you can have a better sense of some of the things I've been talking about. I wanted to get that example in front of you because it's been some weeks since we first looked at agent-based modeling with that very first class session. And I wanted to remind you of some of the features of this sort of modeling so that when I'm talking here about some of the distinctions between agent-based modeling and system dynamics, stock and flow modeling, we will have a better appreciation for those trade-offs on the part of students. So this class talks about three types of modeling methods in with some measure of coverage, with the most coverage being on the two that occupy most of the screen. On the one hand, system dynamics, on the left-hand side here. An approach that I've noted is feedback-centered. We're characterizing the feedbacks in systems, often from a high-level perspective, a sort of top-down perspective, expanding detail where required. It focuses on feedbacks and accumulations. Accumulations being captured by what? By stocks. And the feedbacks involving stocks and flows. Central for discussion because they so, in such a profound way, will often shape the dynamics of the system. The latest problem set, which I also released last week, has an initial problem on it where you're asked to look at a system where the fundamental feedback structure stays the same, but an intervention takes place, which involves what might be called culling, so lowering animal population by hunting and predation or what have you, and a look at sort of the impact of such factors in the context of a feedback system which is still fully operational. And one of the things you'll see is that often adding a flow to an existing system, if you're not changing the feedback structure, it has a limited impact on that system because it's the feedbacks that so shape the dynamics of the system. Shape it in what ways? Well, shape the equilibria towards which the system gravitates, shape the ways in which they shape what of those equilibria are stable and unstable. Unless we can change those things by changing the feedback structure, we're often working at cross purposes with the system. We're trying to force it into a state that's not really a natural one. And if we can shape the feedbacks, shape the balancing loops, the systems that regulate the dynamics of that system and keep it within some balance, if we can focus on those, we can often shape its path more clearly. And it turns out these concepts will come back and help us all through the course for agent-based modeling, as well as some for discrete event modeling. So system dynamics focuses on feedbacks and accumulations. It spans qualitative and quantitative methods. We saw causal loop diagrams used as well as quantitative diagrams, and it supports a rich mathematical analysis. The second problem on the assignment, which is optional for undergraduates, but is something that graduate students pursuing the course assignments will need to think about. There's a glimpse of the sort of mathematical analysis you can do with these systems. And it supports interactive model runs. Model runs that are often quick enough, we can run them in quick succession to help learning. We can modify something and rerun it, modify another thing and rerun it. By contrast, agent-based modeling focuses on interactions between individual actors of one sort or another. They could be people. They might be institutions like companies or organizations. And there's a focus on the interactions between them. It captures the histories and trajectories of these individual actors. We don't simply have a cross-sectional depiction of the population over time, as we do in system dynamics, where we depict the number of people who are in this stock, the number in this other stock, the number in the third stock, without identifying who they are. In an agent-based model, we actually track particular people. We know the stocks that particular person has been to in a way that's not feasible within a system dynamics model. It gracefully represents network connections and nested contexts. Allows us to represent heterogeneity in a more scalable way than in a stock and flow model, and allows for very detailed policy planning. For planning policies, for example, which may treat someone differently based on their history, their past history, based on their position in a network or their location within some broad scope. But it can allow for planning of policies which focus on things at a detailed level. The final type of modeling we'll be talking about will be discrete event simulation, where we're fundamentally simulating the flow of what are traditionally fairly passive actors or individuals through processes, and where those processes depend on resources. So it captures the impact of resources on that flow, and it captures aspects of context, such as physical locations of things, on how quickly those processes can take place. We'll be spending less time on that, but it is something that will be part of our discussions. Okay, having noted those, I'd like to contrast the granularity, as it were, the level of detail, the level of precision involved in the two sorts of modeling we've seen thus far. On the one hand, with stock and flow modeling, characterizing, say, a population among several categories. This depicting the case we had last time, susceptible, infected, and recovered individuals, and also a vaccinated stock and flows amongst them. Here, we have a count of individuals in each stock, but we really can't ask, for example, how many times is the same person, say if we had a flow back from recovered to susceptible, how many times has the same person gotten infected in the population? It's not really set up to answer that question. We can't ask about particular trajectories. We don't know, is it the same person? By contrast, here on the right-hand side, we have individuals depicted in some situated in some context, in this case, a network-based context. Those individuals are associated with histories, biographies, as it were, and Their state will change over time, and their context may have changed over time. They may move, or their neighbors within this network may change. Agent-based modeling is a type of modeling that models a system at an individual level. And it sometimes goes by the name individual-based modeling. In fact, this was the first designation for it, individual-based modeling, when it was first introduced at Los Alamos National Laboratories in the States. They called it individual-based modeling. But that had, for the group of somewhat countercultural Los Alamos scientists there, they felt uncomfortable because the annotation, or the abbreviation, the acronym for individual-based modeling was IBM. And IBM at the time was considered a very straight-laced, pinstripe-suited company that sold things more based on flash and sort of weight of reputation and sort of chumming up to people than it did based on technical merit. So they really didn't want the term IBM attached to their new little methodological innovation. So they ended up calling it agent-based modeling, which is a term that stuck. However, individual-based modeling takes place in many forms. And the term is actually not totally synonymous with agent-based modeling in my view. We can perform individual-based modeling, in fact, in tools like Vensim and stock and flow models. If we were to subscript a given stock, for example, by person in the population, you subscript it, say, by I, so we have we might have a thing here which denotes the number of infective cells in a certain person's body, and we subscript it by I, where I is the population member. Ooh, that's horrible, isn't it? I sub I. Nay to that. So maybe we'll have, uninfected cells, U sub I. Here we might have a vector, conceptually, of this stock arrayed behind it, and we could keep track of individuals just by keeping track of vectors of information of their states. So we have a vector associated with U and a vector associated with, maybe we'll call it N for infected cells, N sub I, and we'll represent the whole population at an individual level with these two vectors. And those vectors represent the amount of uninfected cells in that individual's body and the number of infected cells. In another case, we might have the blood glucose levels of each person in the population, in which case it'd be a G sub I or something like that. But agent-based modeling specifically is a type of individual-based modeling that encapsulates things. Within a single object, within a single sort of sphere of representation, you bundle together the behavior of that person and the state of that person and their characteristics. Those of you from computer science background or have taken computer science courses in object-oriented programming will immediately recognize this. This is nothing more nor less than an object-oriented approach for representing a bunch of individuals. And we can contrast that to ways of doing individual-based modeling in packages like MATLAB, where we represent a population at an individual level as a collection of vectors, where each vector, again, has an element for each individual of the population. So an object-oriented way of grouping this will represent a person as a person object. And that object captures all the characteristics and behavior of that person. And it carries all aspects of their history. So agent-based modeling makes a commitment to the sort of object-oriented way of capturing this sort of information, which is a convenient way of reasoning about it and dealing with it in software. We'll be seeing that a lot in coming weeks. So they provide a very convenient abstraction for individuals. Agent-based models, in contrast to the system dynamics modeling you've been seeing, require at least some code in more traditional programming languages. Thus far, we've been able to get away with putting in place formulas not so distant from the sort of formulas we use in tools like Excel or other spreadsheets, Google Docs spreadsheet. In this case, for current agent-based models, the state-of-the-art in terms of widely available packages still has us doing a lot of programming or doing some programming in languages such as Java. And we'll be seeing some of that. Turns out that we can formulate system dynamics models within agent-based tools, and we'll be seeing that within the next few lectures, probably. And you could say that these models are simultaneously system dynamics models. Maybe each individual in this within this model, for example, evolves according to stocks and flows. In which case it's agent-based and a system dynamics model together. They're not totally in opposition. And we can follow a system dynamics process to build up these sort of models. So a process of the sort we saw early on, where we first do model conceptualization and map out a system in a more qualitative way with causal loop diagrams, and we build towards a more precise formulation. We undergo model testing, etc. Okay, so let's talk about the characteristics, though, that distinguish agent-based models. Perhaps the most central, fundamental, and defining characteristic has to do with they represent populations composed of individual agents. These actors are represented explicitly, and they're represented as objects. We sort of group all the information about one person and their behavior all together in one place that we can go address. Each agent is associated with some state. So these are the typical components of an agent. State, which is some changing status of that individual over time. For example, their age, represented in continuous terms or in terms of discrete categories, age categories. So their age 0 to 4, 5 through 9, or 10 through 14. Well, that's one possibility. Another possibility is that we represent it as a real number associated with units of years. We might represent their health, their smoking status, their network, aspects of their beliefs or preferences as aspects of state. They evolve over time. We also have a representation typically of their parameters, things that don't change over time or change very rarely. Things like their genetic composition. If we're simulating things over a short time, perhaps it's certain preferences or their gender. And then finally, rules for interaction. How do they interact with other individuals? How do they interact just within themselves in terms of their evolution over time, outside of the contact with individuals? And the rules for interactions are traditionally specified using bits, snippets of code in traditional programming languages. Within any logic, we'll be able to do a lot of that declaratively. That is, we'll specify things like state charts. And these state charts will describe the what of that evolution. And we'll, just as we did in the system dynamics packages, where we told it what system we wanted to represent, and it did the job of simulating it, so it is with much of what we'll be doing in any logic for agent-based modeling. We'll specify the what. There's a state chart. There's a stock and flow. There's events, and it will take care of choreographing them and evolving them over time. These individuals, however, do not exist in isolation. They're not solitudes upon themselves. They are embedded in environments, and they typically have localized perception in the environment. They can't see everything. They're not omniscient. They have a very localized view of things. Think about a simulator of a car on a highway. The car and on a twisty highway like you have in the Canadian Shield, say in Manitoba, eastern Manitoba, or in Ontario, where Highway 1, the Trans-Canada Highway, wends its way among various hills in the Canadian Shield and among forests. The car, as it moves along, can only see so far ahead of it and so far behind it. And that will affect its driving speed, its braking behavior, etc. So typically within these agent-based models, there's an emphasis on capturing the fact that that the agents have bounded rationality, and they can only see so far. They can only perceive so much. And their individual decision-making is shaped by the particular information they happen to receive or they happen to have access to. Finally, these agents communicate with one another. They interact with one another through these rules, and the particular mechanisms associated with it are typically with things like messaging. So one agent will message another, will send it a message. This is a general approach we see elsewhere in computer science, such as in distributed computing. And it allows us to simulate these agents in a way we call asynchronous. They don't have to be advanced in lockstep. One could be advancing while the other waits, and the other then advances, and they flexibly communicate via messaging or via flows. These messages might be things like, I have contacted you, so now you're at risk of catching my flu. Or it may be an interaction like, I'm sending you a message to indicate that I would like to purchase something from you. So they're placed within this environment, and from this, there's emergent aggregate behavior, which we can summarize in all different ways. And in fact, ladies and gentlemen, the lens which we learn to apply in system dynamics models of stocks and flows and reason mode feedbacks, etc., ends up applying very, very well to agent-based modeling. Those basic concepts carry over. They're simply more aggregated atop an underlying population, which is evolving at an individual level. Let's talk some, reflecting these sort of differences, let's talk some about the differences in organization between, on the one hand, agent-based modeling, and on the other, system dynamics, stock and flow modeling, when we characterize a population. So I noted that before that agent-based modeling adopts the organizational style of object-oriented software engineering. It clusters together elements of state and behavior associated with these individual actors. Their behavior over time, the current state, their properties, their characteristics. And this facilitates convenient representation at several levels. One is it's, at a conceptual level, it's easy to interact with these things. We look to the object to ask questions about it. In the real world, if we want to find out about someone's biography, we want to find out about their current situation, we want to find out about their characteristics, we naturally go to them. And so it is with these agent-based models. So if we want an agent, for example, to change state in some sort of way, to graduate or to become sick, we direct that request to them, to that object. We say, get sick, or, are you sick, or what have you. But it also allows us to represent nested relationships and network relationships. We can put these individuals in networks, and we can nest them together in hierarchies. So I'd like to emphasize this, a key distinction here. And this is going to cut to the chase as some of the distinctions. So what we've seen when we characterize populations in these stock and flow models we've been seeing, we subdivide the population according to state. If you really think about it, the models that we've been dealing with, models of this sort earlier, and I wish I didn't have to flip back to show it, but this sort earlier, we have susceptible, infected, recovered, and vaccinated. We're counting individuals. We're dividing up the population by state, by their state, putting them in different bins based on their state, and then we're counting the number of individuals in each bin, right? Each bin is responsible for keeping track of the number of individuals in it, right? Make sense? So it's organized according to state, and the information maintained for each of those states is the count of individuals within that state. I'd like to contrast this with a situation in agent-based modeling where we're subdividing the model up. We're organizing it according to individuals. And then each individual maintains its own state, maintains the information about their own state, okay? So here we are dividing up these individuals into these categories. Each stock, the data kept, for each unit in that organization is a count. And the state for different different units of analysis, if we want to have information, for example, at the city level or information for the nation as a whole, those would just be variables in the model. We could have, for example, this count, each of these stocks, we could have a version of them for example, Saskatoon, another version for Regina, another version for Moose Jaw, another version for PA. And then we might have quantities that are sums up over the entire province of the number of susceptibles or the number of infectives or the fraction of the population that's infective, the prevalence across the entire province. And those would just be variables within this model, right? Just be variables in the model. It's all sort of at a horizontal level. The relationships between these units, sort of how much one city contributes or another, is sort of left implicit. By contrast, within an agent-based model, again, subdividing it according to individual, the organization, instead of being according to state, is according to individual. And within each individual, they maintain information about their current state. Their state with respect to one set of characteristics or another with respect to their current properties. That's all maintained within the individual. And nesting of these individuals is done in a way that sort of mimics nesting in the world. So if we have, for example, a city, and within that city lies a bunch of individuals, maybe we have a collection of cities, so we have Regina, Saskatoon, Moose Jaw, PA, etc. And within each of those cities lies a population of individuals. We can represent that naturally by having city agents. And each city agent maintains references to a set of person agents that live within it. And there's a hierarchy between these types of agents from this very low level associated with persons up to this next level associated with city agents, and a next level up perhaps even of provinces. So this would be the Saskatchewan agent. And there may be certain processes which take place at each of these levels. Perhaps processes associated with policy or taxation or what have you, which occur at these different levels. We can represent that, and the nesting is captured. The nesting in the real world, whereby people live in cities, is mirrored in the model. We have a representation of a city agent, and within it is a link to the various people within that city. So there's a contains relationship in the model that kind of mirrors that in the world. So what sort of elements would be part of individual state? Well, discrete elements. This would be state or properties. This could be state or properties. It's actually individual characteristics, because not all of these are truly changing aspects of state here. So excuse me. Characteristics. Sorry. So, for example, at the discrete level, we might have ethnicity, gender, etc. At a continuous level, we may have things, as I noted, age, the amount of body fat in the body, metabolic rate, past exposure to environmental factors, any number of different things. Let me ask this, folks. Suppose that we wanted to, within one of these models, a stock and flow model. Oh, am I going? Within a stock and flow model, we wanted to capture an individual who has different. So suppose that infection progresses. There are certain types of conditions, say TB, where the longer you have it, the more serious it becomes, the more likely you are to have a very serious case that spreads easily, cavitary TB, for example. This is why they used to call it consumption. Once people got it, if they couldn't clear it, it would get worse and worse and worse, and they potentially infect people over time. How would you capture that progression process within a system dynamics model, within a stock and flow model of this sort? Anyone? How would you capture progression of that sort? Progression of infection. So maybe now we don't want to just represent infectives as one category. We want to represent sort of degree of infectiousness. How do we do that?
Multiple stocks.
Multiple stocks. So you'd have several infective categories in ever successively more serious condition, for example. And maybe there'd be higher mortality rates the further you go down. There'd be a worse chance of mortality and a worse chance of infecting someone as well, right? So we could do it, but we divide them up into discrete categories. We'd have to have 2 of them, or 3 of them, or 4 of them of these states. Within an agent-based model, because each individual is keeping track of its characteristics, we can keep track of a double precision value as to how currently infectious they are, how serious the condition is. And that, in fact, might vary in a continuous way. It might vary according to stocks and flows within an individual, say, in a way that would reflect the fact that over time their condition is worsening. In other words, we wouldn't try to capture it in the structure, because remember, in a system dynamics model, the structure, the organization of the structure is by state. So we had to break it into these separate stocks. In an agent-based model, we'd represent as a property of that person or an element of their state that would be described according to whose evolution would be described according to some rules. Maybe it's a stock and flow type of situation, and we could represent it continuously. Age could be represented continuously, for example, metabolic rate, etc. But the change in my body composition as I start eating only McDonald's food, for 3 months. Yeah.
So I'm just thinking, from a time complexity model, these are going to be computationally much more intensive.
Indeed.
Than stock and flow.
Indeed.
So are there ways of mitigating that, or is it just you have to sort of suck it up and improve?
No, you don't have to suck it up, and we'll be talking about this issue. It turns out that there's very substantive scaling challenges that are afforded for both sorts of modeling. They tend to be more pronounced for agent-based modeling. In other words, the performance constraints are more obvious at a practical day-to-day level because for realistic population sizes that we deal with and realistic levels of model complexity, it's often the population size that imposes the fundamental limiting constraint in how fast it can run. System dynamics models, or I should say stock and flow models, have their own scaling issues when it comes to another factor, which is degree of heterogeneity. But what I mean by that is suppose we wanted to have this model for men and women. So we want to keep track of separate coupled, but keep track separately of the number of infective men and number of infective women, susceptible men, susceptible women, recovered men, recovered women. Maybe we're dealing with a heterosexually spread STI, for example, sexually transmitted infection. We want to keep track of the number of each that are infective because they have different times to discover the disease, etc. How would we do that? How would we do that in a model like this? Suppose we want to represent it separately for men and for women. Double the number of stocks, right? Suppose now I wanted to represent it separately for different age groups, say 17 age groups, 0 to 4, 5 to 9, 10 through 14, all the way up to age 80, and 80 plus. So what would I need to do then?
Create separate stocks.
Separate stocks. And if we want to do it for both men and women, now we're multiplying it by 2 for men and women, and then by 17, and so it goes up to 34. And we get into recursive dimensionality. With each successive dimension of heterogeneity, because we're subdividing it by state or characteristics. It says state, but it's really state and other characteristics. I don't know that I can fit the state / characteristics. We're dealing with a situation where the number of categories explodes if we subdivide it according to too many characteristics. That is totally scalable within this sort of context. You just add, if we want to keep track of whether someone's male or female in an agent-based model, how much does that double the model size? No, we just add a variable, right? Okay, keep track of an extra variable. Suppose we want to keep track of their age category. Does that multiply by 17? No, it's just an extra piece of information. It might add 4 bytes to each individual or something like that, if that. So, if you're doing it in a naive way. So in this case, there's a scalability issue with heterogeneity associated with system dynamics models. Normally, the dominant one is the one associated with population size. It turns out agent-based models are going to have an additional challenge, though, which is that they are stochastic, typically. And because they're stochastic, we have to use an approach called Monte Carlo simulation. Yes, so we have to simulate the system again and again and again and again to develop confidence that what we're seeing is not the fluke of one happenstance of one particular run. What we're seeing is some regularity that's coming out repeatedly and robustly out of the underlying system. And that requires often running it many times. Now, that's embarrassingly parallel, fortunately, in a way that running the simulation itself is not. Running the simulation itself, simulating all these agents, we might be able to run that in parallel on different machines, but if one agent deals a lot, you don't want to separate, husband and wife agents on different machines. They're interacting constantly. But you might be able to separate different cities, and have little coupling. On the other hand, running it many, many times, the same model, those are totally independent. You can run them on separate machines. So we can use parallel computation, and we can also use clever strategies for decomposing a given population. This happens to be an area of research for me, and I'd be glad to go on at some length about it. But we'll probably touch on this area in down the road in some other lectures, okay? But great question. Scalability is going to be a notable issue that will be on our minds. And one key thing that we can take advantage of is through dimensional scaling, through techniques that physicists have routinely applied for centuries, we can often formulate scaled down populations. Well, you think about the traditional way of building an airplane. People want to simulate an airplane. The traditional way you do that is you build a scale model that you could put in a wind tunnel, for example. And you build this systematically scaled down model. Systematic is the key word there, because it's not just a linear scaling. You have to scale certain things in dimensionally correct ways. And then you can simulate that in a wind tunnel, and you know how the bigger plane would react. And we can do similar things with agent-based models. We can take a subsection of the population, chosen very artfully, scaling things. You think about, suppose you want to simulate a full population of Saskatchewan and the full extent of Saskatchewan. And we don't want to simulate a million people. We want to simulate it with 100,000 people. You want to scale down the area in a comparable way, which may mean reducing each side of it by square root of 2, so that the density is maintained. And so you have to scale it down in a systematic, carefully done way. But if you do that, you can then systematically relate the behavior of the small population to that of the whole population with some assumptions. So there'll be ways of dealing with it, but it requires thinking, care, and state-of-the-art computation to really push the envelope there. And we'll probably talk about that some more down the road.
Just a quick follow-up.
Yeah.
What does the time complexity function usually look like? Like, I'm sure that it's probably reliant on how complex your model is. What are we dealing with usually?
What we're dealing with typically is something that's between, if n is the population size, it's theta of n to theta of n squared. Between those, it's normally omega of n squared, so it's no more than n squared. Where does the n squared come in? Why would we have to deal with a scaling that goes up quadratically with the size of the population? Why doesn't it just scale with the number? After all, we have 100 people or 1,000 people. Why would we have to do more than 10 times as much work for 1,000 as for 100?
Well, if each agent has to interact with another agent.
Yeah. So if you have dense networks, now we have networks whose size may be of n squared, number of links in principle, right? So if you have dense networks, now we have all these pairwise connections. We don't just have to consider A, B, C, D. We have to consider A's interaction with B, A's interaction with C, A's interaction with D. And so if we have the population size or if we double the population size, we more than double the number of things, in this case connections or interactions that we have to consider. But it's very rarely more than n squared in size, and typically it's closer to n because there's few people in Canada that have had contacts with a substantive fraction of the population. So there's some limits typically to how many people you can interact with. So let's talk about feedbacks. We've been talking a lot about feedbacks at an aggregate level in system dynamics models and stock and flow models of the population as a whole. And this is interesting. And at a stock and flow model of the entire population, we might represent, for example, a situation where we have an individual, we have a stock, which might represent sort of average nicotine exposure in the population. As the value of that stock goes up, the severity of addiction, likelihood of smoking, and therefore it further boosts up that stock. So we have a stock that kind of represents these dynamics at a level, and those might reflect dynamics at an individual level directly. It might be linked to a feedback at an individual level, a feedback that drives Johnny to smoke because he's addicted to nicotine. So some of the types of stocks we have in a stock and flow model at an aggregate level might turn into feedbacks at an individual level. And indeed, often the agent-based models have some very significant feedbacks in them that are sometimes the focus of attention because they shape the system so fundamentally. However, some feedbacks within an aggregate stock and flow model might not turn into individual feedbacks within a person. Instead, they turn into interactions betwixt persons that end up being placed in the same stock of the aggregate model. So here, for example, we might have a feedback, the more smokers there are, the more perceived desirability people have to smoking, or the less stigma, and therefore the more smokers there are. You might say that there's a feedback associated with that, particularly during adolescence. But at an individual level, that might be now interactions between individuals. So the number of people that were all aggregated into that smokers category are, in fact, different individuals within an agent-based model. And this might be, in fact, a spread of interactions between individuals rather than a feedback within a given individual. So some things we've been kind of aggregating up may map to feedbacks at an individual level. Some things we've been aggregating up as feedbacks may, in fact, not be feedbacks at an individual level. We can, within these models, and this is one of AnyLogic's great strengths, and one of the reasons we use it, can represent hybrid models. So here we have, for example, a case of a person whose state evolution is described in part by a stock and flow model. And you can create these totally straightforwardly within AnyLogic. You just plop in stock and flow components into the model, and you can have an agent who evolves according to these things, and then they can be put in networks or put on at certain locations, and they can interact with other agents, etc. On the other hand, we often will represent agents, not always, but often, that have some elements of discrete state, whether they're married or not, whether they're pregnant or not, whether they are live or dead, whether they are infected or uninfected, for example. For many models, we'll treat those as discrete categorizations. So we'll have, for example, individuals who are susceptible to TB, individuals who have perhaps been exposed, and then if they're infected, then they go, and if they develop primary progression, they go directly to active TB disease. Otherwise, they go to a latent state. This would be an example of a state chart, which many of you will remember from UML, for example. And we'll use this to characterize the evolution of an individual within these sort of models. Those individuals will then be placed in context and can then interact. So each of these individuals in these networks may be associated, for example, with a state chart like this, but some of these interactions in the state chart may lead them to communicate with other agents, perhaps, for example, infecting other agents from the situated context. We will further look in this class at irregular networks in which people can be placed. So this is an example, for example, of a hospital setting in which individuals will interact with their environment, and we can keep track, for example, of their use of different resources. It turns out that these sort of models are often done purely through the lens of discrete event simulation, but there are some compelling reasons for combining it with agent-based modeling. During our first class, we saw emergent behavior coming out of an agent-based model. We've seen much within our last few lectures about emergent behavior within stock and flow models. So, for example, we had the simple case of a first-order delay, a stock with a simple flow out, whose probability of transition is given by some alpha, and the stock x, and we have alpha x as the rate of flow out, the number of people per unit time that leave. And we saw some emergent behavior coming out that was a declining exponential, e to the minus alpha t, proportional to that. What's that? Proportional, not an alpha. So, but more recently we saw stock and flow models, nonlinear models, where we had things like outbreaks occurring over time. Those are, in system dynamics, the focus tends to be almost exclusively on what are called reference modes or patterns over time of system behavior. And so you're focusing on the behavior of the system over time with respect to some quantities within the model. That tends to be the point of attention. And often you build the model to explain or to help address particular reference modes with which you're familiar. Within agent-based modeling, the attention is often on patterns over time, but often as well patterns over space or over a network, for example, over topology, who's connected with whom, leaving aside or abstracting away from the geometry where they are, but who is connected with whom, and looking at patterns over that. So in our very first class here, we saw the patterns associated with infection spread over space from a very, very simple model. And we saw how changing it by adding a transition could profoundly shape the types of patterns seen here. The structure determined the behavior, just like it does in a system dynamics model, where that's one of the principles. Structure drives behavior. But in an agent-based model, we have these additional dimensions of space and dimensions of associated with topology, for example, that are aspects of situated context, the context in which the agents are situated. So we see, for example, models where we may have phenomena of infection and infection spread, but that's occurring in a spatial context. And sometimes this can make all the difference in terms of understanding. When I first encountered visualizations of this sort, I had an impulse trained by years of work at the command line level and so on, to wonder whether this was eye candy. And over the years, I've come to realize that the visualizations of this sort, while they can be flashy and distracting sometimes and not really cutting to the heart of things, often they do offer profound insights that you wouldn't have gotten otherwise. I've spent months working with models in system dynamics packages where we represented things broken into patches and what was going on, or people in a network, and come away with only very, very little insight as to what was going on geometrically. You put it into a model which represents things geometrically, and suddenly a big insight emerges that you would never have had otherwise, because you suddenly see it's in front of you. It's just obvious what's going on spatially or in terms of the network spread. So this, for example, is a model depicting a situation here in Saskatchewan, interacting deer, each of which is associated with this nasty so-called prion-based disease, a disease based on these misfolded proteins. And the key fact is that they could be deposited in the environment. Within a system dynamics model, which we had of this sort of situation, we had a stock of prions in the environment. It was a stock, and it built up prions over time. And the more prions there were in the environment over time, the more likely a given susceptible will get infected by them, right? Straightforward. It wasn't until we put it into an agent-based context that we realized that it matters where the prions are. These prions are not being built up just everywhere over the model in some uniform way. They're not being smeared over it, in some sort of uniform, smooth way. They're concentrated. Where are they concentrated? They're concentrated in places that the deer go. And that's important for two reasons. One is the deer that die end up being in those places, and it builds up this prion base. And secondly, the deer that are live and susceptible also visit those areas. Maybe they're a fawn, or maybe they're a young deer, and they visit these areas. It's a congregation area. It's an area of frequent visitation because they need to get water to drink, and they're more likely to get infected than if it were just prions based out here in the hinterlands. So the fact that we had this buildup of this environmental contaminant, this pathogen in certain areas, meant we could get much greater rates of exposure than we would have thought through an aggregate model if we had just represented it sort of as an average across the entire space. So these deer are moving around. They deposit prions during their life. They die and deposit even more prions. And individuals come along and get exposed to them and then carry the infection elsewhere. It gets concentrated in non-uniform ways, and knowing about this might lead you to test in certain places you might not otherwise anticipate. Might allow you to fence off certain regions of high risk while leaving others open that would still allow the deer, say, to drink, and it might be protective in ways you wouldn't anticipate through an aggregate model. So we see in agent-based models, just like we did in system dynamics models, aspects of emergent behavior. The whole is greater than the sum of the parts. There's this surprise behavior. We see this in stock and flow models as interactions between stock and flows. We saw it in some nice little examples just recently in AnyLogic itself for stock and flow models with outbreaks, right? Very nice. In agent-based models, though, we see it not just in terms of this time behavior, not just in terms of behavior over time of the system as a whole, but behavior of interaction between agents and agent and neighborhood. Another matter concerns this issue of hierarchy and scale. The fact that within these models, often we are dealing with quantities where we want to speak about the dynamics not just at one level, at the level of a person, or at the level of a neighborhood, or level of a school, or level of a city. We want to be able to talk about all of them at some level. We can do that to a degree within a system dynamics model, within a stock and flow model. We can have separate pieces of the model for different neighborhoods and represent with variables quantities for the different neighborhoods and total them up for quantities of the city. But they're all imposed at that same level. And it's hard to in a detailed way simulate things at these levels without it getting quite messy at all these different levels. With agent-based models, we can very nicely set up characterizations which occur at multiple distinct levels. So we can capture persons, neighborhoods, schools, municipalities, countries if desired, and we can reason about statistics as they would apply at these different levels and processes that apply uniquely at these different levels, not merely as aggregations, but processes. And the motivation for doing this is the emergent behavior may differ by scale, and certain concepts may naturally take place at certain scales. So when we deal with these individual-based models, we can always aggregate up in a way that the opposite is not true. When we deal with an aggregate model, it's sometimes hard to know what's going on at the individual level. So, for example, here with an agent-based model, we can always total up the number of cases of infection at a given time, and we can watch how it changes over time. This would be quite similar to the sorts of graphs we get out of a system dynamics model. However, the underlying dynamics is described at an individual level, but we can still make recourse to reasoning about stocks here, the number of cases of infection, the number of susceptibles, the number of recovereds, and reasoning about the flows between them. We can actually collect information, how many people got infected in the past time step, and provide statistics on it while still having recourse to the individuals. And we can summarize the status of those individuals, their age, aspects of their education, aspects of their infection history, at a level that's very flexible compared to if we had to map it to certain fixed categories within an aggregate model. Okay, so I've been talking about this, and this is an example of a multi-level model. We'll be seeing how easily those can be built within an agent-based context. So individual cities, say each city has some individuals within it, and those cities are linked by transport connections and roads, etc. Okay, so agent-based models have traditionally emphasized multi-level emergence. How do the patterns that we see emerge at different levels of a system? And we may compare the behavior of a system at these different levels against statistics that we have, time series, other information. So, for example, for those in the health area, we may have longitudinal data available, which follows individuals over time. And in an agent-based model, we can collect that information about the simulated individuals, compare it with the aggregated data, and then we may have cross-sectional data with which we can summarize how many people in different stocks over time. And finally, we may have data that are more about the overall patterns of system behavior. What's the fraction of prevalence across the model? And we can compute those as well from these sort of agent-based models. Okay, so why would we prefer one of these types to another? Well, first of all, it's not an either or. This is not a situation where we have to decide purely between one and another. We often will combine them in the sorts of hybrid models that AnyLogic allows you to build is a great testament to this. We may, for example, have a model of patches of some area, and each patch within it has certain characteristics and is reified as an agent. It's represented as an agent, but within a patch, perhaps it evolves according to stocks and flows. And those patches are connected to neighboring stocks and flows. So maybe this is stocks and flows associated with the number of mosquitoes in the stock. And rather than simulating in the patch, rather than simulating each mosquito in isolation, we have the mosquitoes, and they can migrate to nearby patches, and but they evolve according to the stocks and flows within the patch. That would be an example of a hybrid model in addition to those we've seen here. But given that we have these types of modeling, when would you use one or when would you use another? When are they most appropriate? It turns out there's really substantive trade-offs between them. This is not a situation where agent-based model is going to eliminate all use of aggregate models or it's going to supplant them. They're actually both key. Some of the greatest advantages for aggregate model are listed here. Easier construction, potentially quicker calibration against things. There's fewer moving parts, fewer things to match up, or fewer things to adjust when matching things up, fewer things that could be off. Easier parameterization, again, fewer things that have to be filled in. Formal analysis is one of the key advantages of agent-based models. Now, for those from more mathematical background, this affords us the power to get a lot of insight that transcends any one run of the model. We can analyze behavior of the model in general. We could say what are its possible modes of behavior. How does the location of the fixed points and their stability, in other words, how does the ability of our healthcare system to contain an infection change as we change our assumptions about parameter values? We can reason about that at a formal level with aggregate models. We don't just have to run the model again and again with different parameter assumptions. We can kind of say, oh, for these regions, we should be able to contain the infection. For these regions of assumptions, we should be able to contain it. For these assumptions, the model's saying we're not going to be able to contain it. That's the sort of analysis you can get out. We'll come back to that in a minute because it affords some additional benefits as well. Another benefit is performance. Often aggregate models are far more computationally frugal. We can run them much faster. And this is not a minor thing because often it's by running the model we get insight, gives us ideas about other scenarios to investigate, and we can learn from the model much faster. If we can run it interactively, the learning is enhanced. The insights can come faster and can allow us to explore more thoroughly. There's less pronounced stochastics, so we don't have to run it many times over. Often it's deterministic. And it's often quicker to construct. The final thing, which is not really represented here, but the formal analysis gives us the ability to run tools, to examine the model with formal tools. Some of the tools that we can use, for example, are tools to visualize which loop in a causal loop diagram is most active right now in driving model behavior. So we're simulating the model over time. Which of those feedback loops is most dominant? Which is the one that's really driving things right now? Another aspect of formal analysis will be when new data comes in, we can kind of balance what the model's telling us, taking into account its limitations, with what the data is telling us, taking into account that it's noisy, uncertain, etc. So formal analysis allows us to kind of have this more informed way about balancing what the model's saying with what data are saying. And the techniques are not nearly as advanced yet for agent-based models in these areas. Agent-based modeling does not afford itself right now to a lot of formal analysis. We don't have the equivalent of differential equations to describe individual-based models and reason about them formally. We can't sit down and derive their fixed points, their equilibria. We can't derive the stability of the situation. We cannot prove under what regions it will be stable. We can't generalize about how its behavior will be changed by different values of the parameters. Instead, for individual-based models, for agent-based models in particular, we're typically stuck with running the model on different assumptions because we don't know how to analyze. I don't know how to compute the Jacobian of a bunch of the values computed by a bunch of Java code. I can't take the partial derivative of this with respect to that, of a loop, with respect to a loop of some variable in a symbolic way. Individual-based models offer better fidelity to many types of dynamics. We can represent certain things that are very hard to capture in aggregate models. Fixed delays are one of the most obvious things that we can represent trivially, but beyond that, we can represent processes with arbitrary time durations, etc. We can support very detailed investigation of very detailed policies. So, for example, policies which depend on an individual's history, a particular perception, or particular preferences. We can make use of longitudinal data about individuals over time in a way that we can't from an aggregate model and accumulate that information. We can represent heterogeneity much more flexibly, and we can examine much finer-grained consequences of things. When we see outcomes, we can examine how did it impact this population as opposed to that population. Whereas to do that in an aggregate model, we have to divide up the model by those populations. And often we end up glomming them into the same stock and we can't really ask, well, how fair was the result of this policy with respect to its outcomes? And finally, it turns out agent-based models, it provides a simpler way of describing some causal mechanisms, where we have a broader toolbox we can use to describe things with greater precision. So there's some key needs motivating this sort of agent-based modeling or individual-based modeling. If you need to calibrate against information agent history, capture progression of agents along multiple pathways, not just along one disease, but along multiple diseases at the same time, where the curse of dimensionality would be in place in an aggregate model. If we want to characterize learning by agents and memory by agents, doing so in an aggregate model is very difficult. Or if we want to capture aspects of early history on agents' later behavior. If we want to capture aspects of localized perception among agents, or we're seeking to intervene in, for example, or explain phenomena across network structures. We'll be looking at the impact of things like scale-free networks and small world networks and Poisson random networks within these contexts. Networks are of keen interest scientifically right now because they describe the structure and increasingly the dynamics of many systems we see, and we can readily reason about those in an agent-based context in a way that is typically quite elusive in an aggregate model. We can study interventions which make use of understanding of differences between individuals to shape their outcome. We can capture impact of interventions across many categories within a population. Sometimes it's simpler to describe behavior at an individual level. We know much more, perhaps, about what's going on at an individual level than an aggregate model, and it's easier to describe at an individual level than we might use an individual level characterization. If we want to have flexibility, adding in characteristics of people, taking them out in a flexible way, it's hard to do that in an aggregate model. We'd have to expand across the entire model, make a copy of everything for each value of these characteristics, and then collapse it back down. It affects the entire model. Adding heterogeneity into an agent-based model is much more localized. It's much more surgical. Whereas adding it in, because you're disaggregating by characteristics in an aggregate model, you often have to make changes across the whole model or large portions of that. Sometimes stakeholders find it much more understandable to reason about individual-based models because they're used to dealing with situations at that level. And finally, if you want to describe behaviors at multiple scales. There are a corresponding set of motivations for aggregate modeling. If you want it to execute really quickly, if you want it to describe system behavior across all possible values for parameters. In other words, you need to do some sort of formal analysis to achieve that. If you want to use mathematical tools like control theory, or you want to use tools out of computational statistics like the particle filter or Kalman filtering, or to guide the system over time, it's much easier to do it with models that can be analyzed formally, so aggregate models. If we want to extensively calibrate to a lot of historical data, it may be much faster to do, at least with an aggregate model. If some stakeholders want to work at an aggregate level, they're much more comfortable because that's the amount of detail that they know about the system. If different subgroups have differences that are merely ones of degree, and we can represent them, the average of them, or what have you, if you don't have recourse to any sort of software engineering knowledge, any sort of familiarity with coding, for example, in programming language, or if you have lack of detailed knowledge of many individual level behaviors, you may be speculating a lot in an individual-based model in a way you wouldn't have to with an aggregate model. What are some limitations of agent-based models? There's some significant ones. We don't know how to analyze them effectively. I have no doubt that within the next 50 years, we'll know how to do this. We're working on this here using ideas from programming language theory, and there's some aspects of programming language semantics we might be able to bring to it. But right now, we just don't know how to effectively analyze the behavior, mathematically crisply characterize these models. Another issue is that these models, agent-based models, have long run times. If you need to simulate your model very interactively for stakeholders, you need to have them asking what-if questions with immediate response. Using an agent-based model is not going to be advised. Sometimes calibration, if you want to calibrate your model, match it to data and get an exact situation about what's going on, you're typically not going to be able to have enough information to pin down the state of every agent. Occasionally you will, with some of the types of smartphone-based data collection we do, and we can relate that to individuals in a model. We can sometimes pin these things down, but in general, it's a hard thing to do. There is a requirement for some software engineering, some comfort with doing some programming. We're going to keep this on the more gentle side in this course, but once models get very large, you can get quite large demands in terms of needing to keep track of it, because it's a large program. I work with agent-based models that consist of 75 Java modules. And this is a highly sophisticated model, one of the most advanced in the world, looking at its situation. But it's turned into, for the people who built it, they desperately need software engineering expertise. And that's what I'm bringing to the table. That's not something that most modelers have in their own training. And so it typically takes a partnership to build a very sizable model. Achieving model transparency is difficult. There's a high value placed on the characteristic of being able to fully describe scientific experiments, because reproducibility, the ability to reproduce the scientific experiment, is considered an essential component of the scientific process. If we describe something in the scientific press, we attempt to do so in a way that would allow others to reproduce that phenomenon, to double-check our results, to extend our experiments. It's part of peer review, and it's part of making a scientific description of things. Currently, this is hard to do with agent-based models. Traditionally, it's been even worse. AnyLogic gets you far further along the way than if you were to try to publish page after page of Java code or C++ code to characterize your model. It's much better if you can use declarative specifications where possible, things like state charts. It's much clearer, but we're still not out of the woods yet. And getting crisp descriptions of the models is very hard to do, even with some of the more advanced packages that are excellent, like Repast and AnyLogic. We're working at this here using functional reactive programming and functional languages that some of you will have seen in 340, but it's going to be some time before those penetrate to the mainstream. Traditionally, agent-based modeling has not been as attentive to the agent-based modeling process or qualitative modeling as system dynamics. We've started to adapt these forms to agent-based modeling, but that's still in its infancy. So when it comes to kind of brainstorming with stakeholders about agent-based models, how to build up an agent-based model, often the reality is, well, system dynamics model building can be done in a group and is often done in a social setting in a way that allows people to contribute. Agent-based modeling often is more involves meeting with stakeholders and then going off and someone creating the model in a different venue. So we're working on ways to allow these sort of models to be built in a more widespread fashion, so that lots of people can understand them. Finally, the need to articulate things at an individual level of detail, it sometimes poses challenges, because sometimes you don't understand things at that level. Modeling is useful because it exposes that lack of understanding. It helps bring it to the attention that it needs addressing. But there are risks that sometimes when you go to express things at an individual level, you find yourself falling short in terms of your knowledge, and you find yourself speculating. And you put a lot of effort in to different speculations about what's been going on. You kind of spin your wheels without really making progress, whereas an aggregate model would allow you to sort of get somewhere by abstracting over these details. One of the biggest risks that our students face in learning object-oriented programming, perhaps yourselves, just a year or two ago, when we learn about object-oriented programming in 270 or other classes, sometimes there's these impulses. You realize, wow, I can characterize all sorts of things. We can represent all sorts of information about people as in an object. We can use it in this very flexible way to characterize situations, and that's true. The question, though, is what do you need? What do you need for a software system, and what do you need for a model? And it's easy to get in a situation where you're kind of going back and forth. You can put all sorts of things in the model, but it outstrips your knowledge. It outstrips your understanding of the mechanisms in the real world. And as I said, it can become an exercise in speculation. Sometimes, if that's very bounded, you can still use it to make progress, but sometimes you're better off starting at an aggregate level, identifying the uncertainties, working to resolve them through more advanced data collection methods, and then with that added knowledge, then you can go down and expand that level of detail. So just be aware that our ability to describe using agent-based models, our ability to describe processes using that agent-based models often outstrips our ability, our knowledge of the systems. And we have to be careful about that because it's often not the modeling platform that's going to hold us back, but our knowledge about how the world may operate and our ability to hypothesize in a grounded way about how it operates. This is an issue with agent-based modeling because it's so easy to add in detail. In a way that with stock and flow modeling, it's less of an issue because you're more pushed back again. You're constantly pushing the limits of sort of from a top-down perspective of whether I should add in more detail. So with agent-based modeling, it's something that you face every day. When I was an undergraduate, many years ago, maybe some of you think we only programmed in ones and zeros back then, and the world was yet young. Some of the others out there might think we only programmed in zeros. There weren't even ones yet, but there were. We had twos also. No, we had a lot more than that. We were doing good stuff. But I passed this mural every day in the corridors, and I didn't really make much note of it. But I think it was sometime around when I started grad school. I stopped. This was near the science library at MIT, and I stopped and actually took a look at this. Anyone recognize this situation? It's a blind man and the elephant. An ancient parable, an ancient story about, of course, these blind men, each of whom are encountering these fascinating components of the elephant, and each of them characterizes, perhaps quite accurately, their particular piece of the elephant. This one on the left ear, this one on the right ear, this one on the tail. This other guy has been studying the trunk. And each of them, of course, comes away with a very different take on what's going on. And they spend a lot of time arguing about it. And of course, they're all describing parts of the elephant, this underlying system. And I would argue there's a similar issue that's going on with these sorts of modeling and the underlying systems. Aggregate modeling and agent-based modeling, discrete event modeling, they're all lenses, they're all ways of describing underlying systems. And rather than getting caught up in the virtues or the dominant character of any one of them, we need to recognize that each do contribute some understanding of the underlying elephant. And it turns out that these types of modeling are highly complementary. And AnyLogic is one of the best tools for revealing that complementarity and allowing you to take advantage of it. So each type of systems modeling that we're dealing with here has a different core focus, different questions that it asks. its frame of reference is different. And differences in the types of problems it can and is typically best suited to address. And the different types of modeling can be highly complementary, even synergistic, if you combine them in the same project or even in the same model. Towards the end of this class, we'll be discussing a little bit of the trade-offs more, but more the synergy between these sorts of modeling and seeing how they can be flexibly combined to yield insight within a system, given model, and within your professional lives, ladies and gentlemen. You'll probably be seeing evolutions of these approaches, where some of these barriers we've been talking about today will be lessened. We may develop ways of effectively analyzing agent-based models. We may develop techniques for running those models much more efficiently. We may develop techniques for building them in a very fruitful way with broad stakeholders, so we can involve people at all stages of the process and not merely look to the final agent-based model as the deliverable of value, but something about the process as a whole and changing people's mental models. Similarly with aggregate modeling, we may find more effective ways to use it to scale with heterogeneity. We may find more effective ways to hybridize it with multiple approaches. So within this class, we'll try to give you some glimpse of this, but for the next bunch of lectures, we're going to be focusing on the trunk of the elephant, namely agent-based modeling and aggregate model and individual-based modeling. Okay, so that's all for today, and in fact, all for given the break for a while. I have distributed problem set 2, and I'd urge you to get started as soon as possible. I will be in my office for most of next week, and here next Friday, and I'd be happy to meet with students, either student teams for projects or students about the assignments. It's due not too long after that, so I would suggest that you try to meet with me, earlier rather than later. And I'm going to be actually going and talking about this sort of modeling for the 2 lectures after that. So the Tuesday and Thursday after spring break, I'm not going to be joining you in person. I will be asking you to watch videos and undertake some exercises as part of that. There's some very good videos which are recorded and which you can use to get up to speed with agent-based modeling in any logic. I will then be back after those 2 lectures to continue on our exploration of agent-based modeling. But be sure to get started in the problem set early, and be sure to examine its various components. And finally, if you didn't do the little assignment for today, please start it within a few days of this, because I think you'll start to see some of the points about how any logic characterizes these agents and groups together behavior and state. You'll start to get some understanding of that. Okay? Yes?
That exercise you speak of, is that what is called exercise 2 on the website?
Oh, that's right. That's exercise 2. Yeah.
Okay.
Exercise 1, for example, was this one with the SAR and vaccinated. Okay?
Thanks.
So if you could check out exercise 2 there, that's great.
I haven't looked at it, but what kind of interfaces any logic after kind of defining it? Because I mean, I caught that.